Welcome to this webinar. My name is Xiaoli Song from Altair Support Group. Today we are going to talk about OptiStruct superelement. We are going to cover what are superelements, why use superelements, and then we will also talk about superelement theory. I will also show how to generate and use superelements. So this presentation will take about 25 minutes. If you have any questions, please feel free to type in the chat window. So superelement is an industry standard technology that helps us condense out inner degrees of freedom of a model and reduce the model to specified outer degrees of freedom. Let's take this vehicle trim body as an example. So the mesh model might consist of millions of grids, and using superelement, it can be reduced to interface nodes with matrices being attached. So the interface nodes can be nodes used to connect with suspension, can be acoustic response, can be vibration response points, and the matrix can be stiffness, damping, mass, and loading. Sometimes people also call it DMAIC. So it stands for Direct Matrix Input on Grid. Basically, the DMAIC stores matrix name, grid ID, and matrix entries associated with a grid ID. And using the grid ID, the superelements can be connected with other superelements or the remaining FE structure. Then we can form a residual analysis. Because the size of the superelement is much smaller than the original mesh model, it can be reused efficiently in residual analysis. On left side is a non-superelement silver deck or the original silver deck before using superelement. Here I assembled trim body, cavity mesh, and other modules of suspension. Then I reduce cavity and the body into a single superelement. Then in my residual analysis, I assign the superelement and delete trim body and cavity model from here. This is how we use it typically. So why do we want to use superelements? Many reasons. A complex structure like airplane or vehicle, it can be partitioned into many modules. Then the superelements can be created individually by different groups before being combined to perform a complete analysis. Or if a large analysis has so many degrees of freedom, time steps, frequencies, or nonlinearity that makes it so difficult to finish. Using superelements, because we can solve the structure part by part, it's possible to finish the analysis with much less resource. So in this way, we can reduce computing costs. Also, using non-superelement method, processing big model means a huge investment of time and computing resource. If we made a mistake in the middle, the entire model has to be processed again. Using superelements, only the affected module has to be reprocessed. Moreover, superelements offer us an option to define the model as a black box. Then we can keep geometric details confidential. So there are several types of superelement. We are going to make a summary at the end of the presentation, but let's focus on CMS method first. It stands for Component Mode Synthesis Method. OptiStruct supports static condensation, which is also called Gaussian method. We support dynamic condensation using CBN GM method, and also flex body condensation using CB and CC. This can be used for NBD-based analysis. All right, now let's move on the theory part. Here, for this trim body, we need to define inner degrees of freedom and outer degrees of freedom. For this inner part, we want to condense out or omit. For outer degrees of freedom, these nodes we want to keep because we want to use it for connection, response definition, loading and constraint definition in the subsequent residual analysis. With this, the displacement vector can be partitioned into UO and UA. Accordingly, the static equilibrium equation can also be partitioned. Okay, let's expand on this point. With this partitioned equation, the first line reads as this times this equals PO. Reorganize it, then we can achieve the inner degrees of freedom displacement UO equals the right side. And the second line, this times this equals PA. Then let's plug UO into this equation and reorganize it to obtain an expression in this way. So this one is very important because it can be interpreted as K reduced times UA. So UA is the outer degrees of freedom displacement equals P reduced. Now we know we can use this transformation to reduce our stiffness matrix. K reduced can also be written based on displacement matrix S. So we S transpose times K. K is the original the matrix stiffness. Times S equals the part on the right side. In OptiStruct, S is generated through static analysis. So here I want to say this transformation is an equivalent form on the transformation on the right side. So this is Gaussian method. We obtain a transformation S, which consists AS with this previous partition and reorganization. We obtain this transformation. Then we can reduce stiffness and the matrix. In dynamic reduction, besides AS, an eigenvalue analysis is also performed. Then in displacement matrix, we will have two parts, A omega and AS. So the A omega is a matrix of eigenmodes. The best practice is when we ask OptiStruct to calculate the eigenmodes, we should set the frequency upper bound at least 1.5 times of the frequency range of interest. Then we can form a good model space. AS part is static modes. It's the same as the one we get using Gaussian method. So in Gaussian method, only AS, the static part. In dynamic reduction, we have two parts, eigenmodes and static modes. So the reduced mass matrix is accurate using dynamic reduction. On left side, because using Gaussian method, eigenmode is not calculated, the reduced mass matrix is not as accurate. Then it should be used only for static analysis. All right. Let's use this simple model to do some hand calculations. It's helpful for us to understand the theory better. Here I have two springs, two nodes. I want to define this as inner degree of freedom. This is outer degree of freedom. I also have an internal load applying on node 1. We construct stiffness matrix, plug in the values, and partition the stiffness matrix. Then we're using the transformation function we got in previous slides. Then plug in the values. We can have the solution for K reduced and P reduced. At the end, we can put these values into this black box with a node 2 as outer degrees of freedom. So by this point, using this transformation, the reduction run is completed. The super element is ready to be used again and again, unless we want to change something inside. Now let's bring this black box to combine it with another module to form a residual run. Here, x2 is unknown. Then the static equation can be written easily. We plug in the values, the solution for x2 is obtained. It's 5/3. This is residual run. If we compare it with a non-superlative run on the right side, we can see that we have same results for x2. So up to now, we finished residual run. So in this residual run, we have the solution for x2. But what if I want to know the solution for x1? x1 is the inner degrees of freedom we condensed out, right? Actually, it's not always necessary to calculate this. But if we need it, we should use the results recovery technology. In previous slides, we got this expression for UO, the inner degree of freedom displacement, by partitioning days, reorganizing days. We can see that there are two parts. This part is due to internal loads, PO. Second part due to the displacement of UA, the outer degree of freedom. In this case, it's x2. With this expression, we plug in the values, then the displacement of x1 can be recovered. If we compare with the results using non-superelement, you can see they are the same. All right, this is all of the mathematical part I want to share with you. Hopefully, it covers the basic theory background. Okay, let me use a simple model to show how to set up a static reduction run. Import the trained body we shown in previous slides. I already defined a grid set that has 16 nodes. The nodes is used to connect with suspension and also the vibration response node on the floor. Here, let me define a load collector for CMS method. Because I want to have a static condensation, then I choose gain. Then I create another load collector to define the boundary condition. Here I use boundary fixed. It's equivalent to a set, and select the set with 16 nodes. Then obstruct the nodes. These 16 nodes are the interface grids. Then create a generic load case. Not necessary to specify load collectors here, because I don't have SPC or MPC here. We need to create a global case control to reference the CMS method card we created just now. Okay, then I also want to delete the omit card. Then it won't mess up my analysis. All right, then it's ready to run. The OptiStruct will condense this model and reduce it to the interface grids, to the 16 interface grids. Once it's done, we can see the H3D file and also this out file. From here, we can see many information. So in Gaia method, no eigenmodes is calculated. You can also see the information of this matrix. Because I have 16 interface grids, each grid has 6 degrees of freedom. My matrix size is 96 times 96. All right, this is a demo. So by default, the superelement format is H3D. So once we have it, in our residual run server deck, we can replace the original mesh model with our H3D file. Then nothing is duplicated here. I think this is straightforward, right? Of course, In the server DAG, we also need to define connection elements, how to connect tire with a suspension, how to connect suspension with our train body. But here I didn't show it. So generally, there are two methods to incorporate CPR elements. First method is assign. We assign the H3D file. We also need to give it a unique name. Method 2 is using include command. We include the punch file. Punch file is a very commonly used format. So in the punch file, the demig name and the grade IDs are defined. And we also need demig commands lines to reference this name to this type. So this is a stiffness matrix. We let the server know that in this punch file, the matrix with this name is stiffness matrix. Similarly, we can define matrices for other parts. Other stiffness matrix may have a different name. Mass matrix damping can also be defined. Then let's have a look at the comparison between different DAGs. So for Gaussian method, here I reduced the train body. I use Gaussian method. This should be specified in CMS method card. I also need to define a boundary fix. This is static. For dynamic, here I changed to CBN. Remember, for dynamic method, an eigenvalue analysis is performed. So here I specify upper bound frequency for the model analysis. Here I also need to specify a S-point ID to store the eigenmodes. All right, if we want to condense structure and cavity together, we need to include cavity mesh and define the lines for cavity, the upper bound frequency, and also the IDs to save cavity modes. Also, we want to let the server know the interface grids for cavity. So these are two response points of cavity. Okay, let's have a look at this table where I highlighted the difference of the methods. So Gaussian is suitable for only static analysis, and CBN is recommended for most dynamic analysis. CMS GM, in this method, OptiStruct run an additional eigenvalue analysis that is performed on the reduced matrix. The matrix is always diagonal. So that's why it's recommended for model participation analysis. And the CDS, using CDS, the residual run can be finished faster than the CMS, but it's only supported for direct method. So many users use this method to perform DOE analysis where we have many samples. And in OptiStruct, we have 3 super-element strategies. So this method is using same theory. It's just a different automation process. Just now, we introduced external super-elements. There are 2 parts, generation run and residual run. Second method is the internal super-element. It has only 1 step. Means generation run and the residual run are performed at the same time. Here we use SE set to define inner grids. Remember, in external super-elements, we define interface grids, but here we define inner grids. Third one is the part super-elements. These super-elements are defined in each partitioned bulk data section, and the same IDs are allowed across different parts. All super-elements can be copied and repositioned. Here we can have a look at some frequently asked questions. So what format is supported? By default, H3D, and we also support Punch and third-party software. What kind of boundary condition, SPC, MPC, preload, static loads can be specified using CMS method card. And what is S-point ID? It's used to store structure eigenmodes. And what boundary condition should I use for outer degrees of freedom? We should use the one that better capture the model behavior when it's assembled. So there is some theory. If it's fixed, then a unit displacement in each interface degrees of freedom is applied with other degrees of freedom fixed. It's free, then OptiStruct will run some initial bit relief in reduction run. Using plot element, we can save a lot of time for solution and for post-processing. And also ARMSYS is supported. The silver element generated using ARMSYS is supported by Lensos. And it's a standard solver of OptiStruct, which doesn't need any additional license. Damping, I want to highlight that by default, param G is not reduced. If we have this class specified, it can be reduced. The global damping can be applied in the entire model in Residual Run. And to enable stress and displacement recovery, we need a model card and a stress displacement output request card. To relocate external superelements, we can use demake mode. It's supported by nonlinear analysis. Then the nonlinearity is applicable for the residual model. For the demake part, it's only linear. So in this way, we can speed up nonlinear analysis. All right, I think we are running out of time. Today we reviewed what and why, we discussed the theory background, and we show how to generate and use it. The important part is we need to split the model to generate a model containing only the part we want to reduce. And then we need to identify outer degrees of freedom. Then for static, we use Gain. Dynamic, we can use CD and GM. Once the H3D file is generated, it's ready to be assembled with other model to have some residual run. Okay, hopefully this webinar is useful for you. All right, thanks everybody. Thanks again. Thanks for your attention. Bye-bye.